Hello everybody, welcome to my presentation for dynamic programming, the concept of memoization and time complexity. This is part of my project for my course CS131 in Discrete Mathematics by Professor Yoon, and my name is Oliver. In this presentation we will go over the concept of recursion, the concept of dynamic programming, and you will see that those are pretty close together. We will talk about memoization, what that is, and pretty much that this is the main idea of dynamic programming, and then space complexity, which is also another idea like memoization. Let's talk about the concept of recursion. I have a very simple code here that is called print fun. Print fun pretty much lets us enter an integer. Let's say, for example, here we have integer 3. And we use this integer in our function. If the integer is less than 1, just return it, else we will get our cout. I use C++ for this. We will have our number, and then we call the function again, which will call the previous term and will also then display the previous term. Pretty much what we have down here. A recursive function, by definition, is a function that keeps calling itself, right? So we call the first number 3 of this integer, then we get the previous one, and we get the previous one, and then we go back 1, 2, 3. We can see this over here in our function. We first start, we call it 3 times. We get, when we call it the first time, right? 3, previous term is 2. And we go here, we call this again. We check all of our cases here. It is not less than 1, so therefore this else statement happens, and we will call the function again, which then will display the next number. And then number 1, we will return this one again. That's why we have the 1 here. We'll call it again. We go back up, and so on. That's pretty much the whole concept of recursion. It's a function that keeps calling itself and that has a very straightforward approach to solving any problem here. Probably one of the most famous or well-known sequences or recursive problems is the Fibonacci sequence. Pretty much we have covered this in our book, but I'm just going to go over it real quick. The Fibonacci sequence adds up 2 terms, the first 2 terms, and computes the third term. Then it would add up this one and this one to compute this term, and so on. Alright, this is pretty much what we have here in the code. This function here receives an integer n. If this integer n equals to 0, we will return 0. If integer n equals to 1 or integer n equals to 2, we will return 1, because we have 1 and 2. They're both, because right, this is 0, pretty much 0 plus 1 equals 1. 1 plus 1 equals 2, right? Okay. And then we have, otherwise, if n is greater than 2, right, we have return the Fibonacci sequence from the 2 previous terms added together. And we will see that the first 5 Fibonacci numbers are 1, 1, 2, 3, and 5. However, there is a problem with this if we are looking at time complexity, right? So let's check this out. We are using this function again with our number 5. First, we go down here. We have number 4. Recursive problems pretty much are using your problem and making it into smaller problems. As you can see here, we always break the problem down to smaller problems, smaller steps. So there is a lot of steps actually to find all of the numbers for the first 5 Fibonacci sequences. Now imagine you want to find the 5,000th term, yeah, 5,000. That is going to be really hard. It's going to be a lot of arrows. So that's where we actually use dynamic programming. All right, let me step back for 1 second here and explain this one more time. As you can see, we have f of 3, fib 3, like the number 3, called twice by the function. All right, but what if we tell our program to store this number, and anytime we need the function value for 3, we get it out of an array, okay? Because, again, for 2, we have 1, 2, 3 times. Therefore, the time complexity here goes 2 over n, and we learned like big O of 2 over n is quite, like, even though it's fast with processors these days, it's not as fast as we could make it. We could make it way more dynamic and therefore smarter, the program. Just make it smarter. And let me tell you, I'm going to show you how you can do this with only 1 line of code. And that's kind of interesting because if you think about it, 1 line of code can change a whole program. This is the same code, but what we are doing now is we actually call, let's say, an array. Let's initialize this. It's called memo. And once this is initialized, this array, we say memo for a position of number 2 equals 1. That's the value, right? This one equals this. We know it. We can save it. The same for memo of 3. The value will be 2. Right? 1, 1, 2, 3. Remember, that's the sequence. So value 1 will be 1, value 2 equals 1, and we add these two together, and that will be the third value. This will never change because it's a Fibonacci sequence. Therefore, if we just save it in this array here, the computer can always just go straight to that memory location and insert the value without having to do this whole term. Right? This would actually be what we would have to use here. We don't. We cancel it, and so it's a straightforward approach. It cut the whole, if you look at it on the previous one, it cut this whole area pretty much out. This is all gone simply to the memo that we used. Now the thing here, before we go look at the code, is the time complexity here is now cut pretty much by a root. We use that to now have only O by n, which is one of the best time complexities you can have. It's a huge improvement in processing time, and this is pretty much just a simple example of how dynamic programming can change algorithms to be more efficient. And in an age of technology where technology is just going faster and faster, I think that these concepts will help you to, get a better job at the end, because you know how to cut it down, like the processing time, by quite a bit. And the way we do this here is, remember, this is our Fibonacci function from before. We use here, we just extend, and we use an integer array that I'm just going to call it, I'm going to keep calling it memo, okay? Memo, right? Here. Okay, so this integer array memo will pretty much be used for this line of code, which we will put over here. So let me go through this code. What does this code mean? Memoization is pretty much the process of storing the integer value for Fibonacci numbers that we already know. Like if we want to compute Fibonacci number 3 back here, we already know this whole step. So therefore, we stored the value, and every time we have to use that value to find the new one, and remember, we always have to use the previous two terms to find the next term. Therefore, it's kind of smart if you don't have to do an extra calculation on the side here. You can just plug in that number, and that's exactly what this line of code does here. The else if tells you that we take the variable n that we plug into our array location, and this array pretty much consists as well of the previous two terms, and it saves it in the array. Therefore, the computer can always just get back, grab that information, and doesn't have to use any processing time. The last thing I want to talk about is space complexity. This is the concept when we use recursion and dynamic programming and try to limit the amount of code that we write and limit the amount of ways and paths that the program has to take, because the more code we have our program run, the longer it will take, right? The more memory it will use. So this is pretty much helping us to allocate the most time complexity and the most programming power for our program, the most efficient, I would say. So here we have the concept of just storing the previous two variables and forgetting about everything else. So you pretty much just do the same here. We have a equals 0, b equals 1, and c equals I. If n equals 0, return a, which is 0, and then for I equals 2, while I is less than or greater than n, we increment I, right? So we get the next number. So c is a and b, right? So the third term is 1. A equals b in that case, and then b equals c, and we return b value at the end. Therefore, this cuts it even more in half of what we have to write, but it's still the same time complexity. That concludes my presentation. I hope you had I hope it helped you guys to understand a little bit more what dynamic programming means, and that it's not rocket science. It is simply trying to manage the computer capacity and computing power of your program and make it more efficient. Thank you very much.